Okay, so we're back and we're gonna start opening and working with files, yeah. We'll start off with a really simple program that opens a file called girlfriend.txt, which contains a verse from Avril Lavigne's #1 hit, Girlfriend, and just prints it out to the terminal. Here is the girlfriend.txt. Wait, didn't we read this last time? Oh, we can go from here anyway. Hey, you, I don't like your girlfriend, no way, no way, I think you need a new one. Just... Is she talking about herself, right? She wants to break up your relationship, and she's a homewrecker, right? That's just a teenage homewrecker, I suppose. Yeah. And here's our program. Import system.io main do. Right, we've already done this in the advent of code, but right, main do. We create a handle which is open file, and the name of the file. This is a relative path, I assume, because the girlfriend.txt exists within the same directory. And we open it in read mode because we read the file. That's our handle. We bind our handle to opening the file in read mode. And then we extract the contents, kind of, which we get handle get contents from our handle. This will be... Right, this here is an IO string of all the contents of the text, while the contents themselves will be a string. Right, we unbox the IO string. Oh, this is the IO string, and we use this function to unbox it, I think. Right, and then we print... Oh, close handle. That is something I have not been doing yet. I had not been thinking about doing that. Yeah, the handle, close, handle. That's quite important, isn't it? Running it, we get the expected result. Run Haskell girlfriend.hs, and we just... yeah, we print the string. Let's go over this line by line. The first line is just for... exclamations to get our attention. Wait. 4 exclamations? Right, in the second line, Avril... Oh. Right, I get it. He's getting our attention. Hey, you. That was actually quite funny. Alright, in the second line, Avril tells us that she doesn't like our current romantic partner. The third line serves to emphasize that disapproval, whereas the fourth line suggests that we should seek out a new girlfriend. Let's also go over the program line by line. Actually, I think that was one of the funniest jokes so far in the text. Our program is several IO actions glued together with a do block. In the first line of the do block, we notice a new function called open file. I wonder what this function does. This is its type signature. Open file takes a file path and an IO mode and IO handle. Right, that's our handle. We named it handle. IO mode was read mode, yeah. If you read that out loud, it states open file takes a file path and an IO mode and returns an IO action that will open a file and have the file's associated handle encapsulated as its result. File path is just a synonym for string, simply defined as the string. IO mode is a type that is defined like this. Alright. What modes do we have? We have read mode. That makes sense. Write mode. sense. Append mode, alright. Write mode, I think I've cheated on this a little bit because I already know what these do. This is just reads the entire file. This writes from the 0 point, so everything that's already in the file will just break. You will start with an empty file, so to speak. So whatever you write within your program, that is going to be the file. Append mode is where you add at the end of the file. Read write is, I assume, that you edit. I wonder if you can edit lines and whatnot, or if you just read the file and replace everything, like write mode. Don't know that, but we'll see. Just like our type that represents the 7 possible values for the days of the week, this is just an enumeration that represents what we want to do with our opened file. Very simple. Just note that this type is IO mode, and not IO dash mode. IO dash mode would be the type of an IO action that has the value of some type mode as its result. But IO mode is just a simple enumeration. I don't get why this is... I guess we'll get to it, yeah. Finally, it returns an IO action that will open the specified file in the specified mode. If we bind that action to something, we'll get a handle. A value of type handle represents where our file is. We'll use that handle so we know which file to read from. It would be stupid to read a file but not bind that read to a handle, because we wouldn't be able to do anything with the file. So in our case, we've bound the handle to handle. In the next line, we see a function called hGetContents, which is handle getContents. It takes a handle so it knows which file to get contents from and returns an IO string. An IO action that holds as its result the contents of the file. This function is pretty much like getContents. The only difference is that getContents will automatically read from the standard input. Right, hGetContents gets contents from a file, while getContents gets from standard input. Like that, yeah. That is from the terminal. Yeah, exactly. Whereas hGetContents takes a file which tells it which file to read from. In all other respects, they work the same. And just like a getContents, hGetContents won't attempt to read the file at once and store it in memory, but will read it as needed. That's really cool because we can treat contents as the whole contents of the file, but it's not really loaded in memory. So if this were a really huge file, doing hGetContents wouldn't choke up our memory, but it would read only what it needed from that file when it needed to. Right, and since it's a lazy language, because I was thinking that if we do... Oh, for some reason I'm tired today. If we do lines on this, we have a list of strings where every string is the line, right? But Haskell is a lazy language, so we won't actually... Right? It's still lazy, so we still haven't read the entire contents of the file. It is just when we actually print stuff we read the specific stuff that we need to read into memory. Note the difference between the handle used to identify a file and the contents of the file. Bound in our program to handle and contents. Exactly, the handle is just something by which we know what our file is. If you imagine your whole file system to be a really big book, and each file is a chapter in the book. The handle is a bookmark that shows where you're currently reading or writing. a chapter, whereas the contents are the actual chapter. And that makes sense. I don't know if handle is the best name, but it works. It works. Right, with put string contents, we just print the contents out to the standard output, and then we do hclose, which takes a handle and returns an IO action that closes the file. You have to close the file yourself after opening with open file. I've not been doing that. I gotta start doing that. Another way of doing what we just did is is to use the with file function. Oh, that gotta be the same way that Python does it, right? So we don't have to close it. We just do this with our file. Right, it has the type signature of file path, IO mode, and then handle to an IO action, to an IO something, and another IO something. Alright, it takes a path to a file, an IO mode, and then it takes a function that takes a handle and returns some IO action. Right, so this is takes a handle and returns some IO action. Right, so we within our with file, this is our function, right? We create our handle and then we do our function, I guess. What it returns is an IO action that will open that file, do something we want with the file, and then close it. Yeah, exactly. The result encapsulated in the final IO action that is returned is the same as the result of the IO action that the function we give it returns. This might sound a bit complicated, but it's really simple, especially with lambdas. Here's our previous example rewritten with to use with file. Alright, with file, boom, we get all that. And then we make a lambda function. Right. So, where was our previous example, right? Yeah, it's all... This whole thing becomes a lambda function, but I'm assuming this disappears just at the end of the parentheses. Check it out. All right, so this is our lambda, which is do. Right, we have to do a do because we're in a new function, which we just bind our contents to handle, and then we put string contents. Wait, wouldn't it be better to put string contents outside? No. We only have access to contents while we are reading the file. When we're outside of the parentheses, the file is closed, so we don't have access to the contents anymore. It's just, we take with file. Yeah, right, we encapsulate this within our with file, so that's... We don't have to close it, because the close happens automatically as soon as we're outside of our parentheses. I kind of like that, yeah. It's the same as in Python. As you can see, it's very similar to the previous piece of code. Yeah. Handle, that's our lambda. Right, and our handle, I almost missed that. That's just, we just get the handle from this, I suppose. Right, it's the function that takes a handle and returns an IO action, and it's usually done like this, with a lambda. Right, because we take, yeah, This is our handle. The reason it has to take a function that returns an IO action instead of just taking an IO action to do and then close the file is because the IO action that we would pass to it wouldn't know on which file to operate. This way, with file opens the file and then passes the handle to the function we gave it. It gets an IO action back from that function and makes an IO action that's just like it. Only it closes the file afterwards. Here is how we can make our own with file function. Alright, how does that look? With file, we take a file path, we take our IO mode, and then, right, take our function, our handle into our action, right? And this is our IO action, right? Do, because all of this it's the do thing. And we return an IO action. Wait. And since we're printing a string, right, the last thing here is just a dot, right? That's nothing, I think, maybe. Yeah, return the result. Our result is... The result from put string is a dot, right? I think so. I don't completely remember. Yeah, the empty tuple, I mean. Right. With file path mode F. Okay. Path mode. Wait, that's our path, that's our mode, and that's our file? Let's see, do. Handle is we open file, path, and mode. Yeah, exactly. That's what we need. Result is F handle. What is this F thing? That's a function. Right, and then we close the handle, and then we return. Oh no, we do return the result. That's interesting. We can close the handle before return. Okay, let's get the explanation here. We know the result will be an IO action, so we just can start off with a do. First we open the file and we get a handle from it. Yeah, that's what we're getting. Hello, Cole got in on tap. Nice to see you again. How are you doing today? Alright, so inspiration today is pay attention to how your skin is straightening. I don't even know. Should sit straight. Yeah. Make my back straight. That's pretty good. So I guess it was a little bit, if not inspirational, good reminder. Alright, so we know that it will be an IO action, right? That's why we do the do. Nice. Then we apply handle to our function to get back the IO action that does all the work. Yeah, that's the same we did before, right? That's the handle. This is our file. Right, we bind that action to result, close the handle, and then return the result. That is so weird, because it kind of said, right? It kind of said that this is a lazy... This does not get saved in memory. But we're doing actions here, right? So how can we close the handle and then get the result? Right, by returning the result encapsulated in the IO action that we've gotten from F, we make it so that our IO action encapsulates the same result as the one we got from F handle. So if fhandle returns an action that will read a number of lines from the standard input and write them to a file, and have as its result encapsulated the number of lines it read, we used that with file. The resulting IO action would also have its result as its result the number of lines read. Right. Okay, I get it now. This here but how does it print? It doesn't print, right? It's our function, I suppose. Is that it? Oh, right. This function, it's this whole thing. Yeah. That's this function. Now I get it. We do the function on our handle, right? Just like we do here. We have our handle, and we put the contents as our handle, and then we put string. So that means our result, if I remember correctly about put string, I don't remember the result, but I think it's an empty tuple. And that's why we close the handle, because that's... This whole thing is the function. It's the lambda, right? Yeah, it's the lambda. There we go. Coleman122 says that image to the right looks kind of cursed right now. Oh yeah, this one? I feel like all the images looks cursed. I guess partly it's my my dark mode. They all look kind of cursed. Right. So if the fhandle returns an action that will read a number... Yeah, exactly. This is with file. Exactly, because we close and then we return the result. That all makes... It is the dark mode? Yeah, probably, right? He's not supposed to have black eyes. He's supposed to have white eyes. I can see the normally black part of the eyes is still there. Yeah, it's right here and here, right? Right. Just like we have hgetContents that works like getContents, but for a specific file, there is also hgetLine. Ooh, I'm assuming that takes a number. hputString. Oh, right, it's printing all the contents. It's gotta be that way, right? No. I don't know. We get the contents and bind them to something. But this, oh yeah, this must be printing the entire contents. Well, GetInOnTap says, it is somewhat cursed without dark mode. yeah, it's somewhat, but it gets worse. And then we pick a specific line to print. And then we can get a specific character. By index, maybe? They work just like their counterparts without the h. Only they take a handle as parameter and operate on that specific file instead of operating on standard input or standard output. Example, put string ln is a function that takes a string and returns an IO action that will print out that string to the terminal and a new line after it. hputStringLine takes a handle and a string and returns an IO action that will write that string to the file. Oh. No, it will actually put it in the line, in the file associated with the handle, and then put a new line after it. In the same vein, getLine takes a handle and returns an IO action that reads a line from its file. That. You posted it without dark mode to Discord. I don't think I've got Discord opened. I have it on the phone, so I can check it on the phone, I guess. Yeah, it's a little bit cursed, but it's not that bad. I guess that is a problem with Qt browser. I don't think it's easy to switch from dark mode to not dark mode. Actually, let's do that. Dark. Is it not called dark mode? What is it called then? Is it set dark? Dark mode. Right, there we go. Colors.webpage.darkmode.enabled. That's the one. Dark. And we set it to false. And then we kind of have to reload. Still didn't do anything. Probably set something. Yep. Set dark. That didn't do anything, right? Right, set dark mode enabled. Current value false. But we want it to be true. I don't know. Did we finish this thing? I think so. Yeah. Loading files and then treating their contents as strings is so common that we have these 3 nice little functions to make our work even easier. Oh, we do? Right. Read file has the type signature of file path and then an IO string. Oh. Remember, file path is just a fancy name for string. Read file takes a path to a file and then returns an IO action that will read that file, lazily of course, and bind its contents to something as string. It's usually more handy than doing open file and binding it to a handle and then doing hgetContents. Here is how we could have written our previous example with read file. I think with file is probably the best one, right? To close. Or do we... Yeah, because it doesn't close the file, right? Because we don't get a handle with which to identify our file, we can't close it manually. Oh, so Haskell does that for us when we use read file. Oh, wow. So that's definitely the one. Why don't we always use only this one? Oh, because read file. And write file does the same. Yeah. Takes a path to a file and a string to write to that file and returns an IO action that will do the writing. Such a file already exists. It will be stomped down to 0 length before being written on. Here's how to turn girlfriend.txt into a caps locked version and write it to girlfriendcaps.txt. Colgitinotab says, when I read this chapter for the first time, I found it rather funny that the author went through the verse from girlfriend line by line. Yeah, I didn't get it first. I was like, what is he talking about? What are you talking about for exclamation? But then I got it. And yeah, like I said before, I think that was the funniest joke in the book so far. The joke that I found the funniest anyway. Right, import system.io data.char. All right, because we want to do them to upper. Main do contents. A read file, then we write a new file, and then we map to upper contents. Yeah, look at this. Oh, that's beautiful. Look at it. Just beautiful. I like this. Right, and then we run it, and then we print it out, and now it's all caps locked. Append file has a typed signature that is just like write file, only append file doesn't truncate the file to 0 length if it already exists, but appends stuff to it. Let's say we have a file, todo.txt, that has one task per line that we have to do. Now let's make a program that takes a line from the standard input and adds that to our to-do list. Right, to-do item, we get line, sure, someone prints out what to do. And then we append to our file, todo.txt, where we just... Right, and we add a new line, because you have to add a new line. That's... I'm curious. It doesn't say, does append line add a new line before? Or does it just append exactly where it is? That's actually, someone noticed that, right, when they were looking at my files, that I did not add an empty line to the end of my file. Isn't it better practice to always be responsible of adding a new line before you append something to a file, instead of assuming that there will be a new line on your file? Yeah, it depends where it is. Wouldn't it be better practice if this always started with a new file, a new line, before the to-do item? Right? Instead of this way, we would have the new line first and then the to-do item. Or even just have as append file that it adds a new line. Shit, but if you don't want to add a new line... Right, no, so not in the function, but maybe having the new line before, not after. Best practice, instead of, right? This assumes that someone else added a new line. And people are not trustworthy, so it's better that you just add a new line yourself. Well, continuum tab says no, because then you couldn't add on the same file. Of course you could. You just trade places on these two, right? You take new line plus plus to do item. Oh, yeah, you mean that we couldn't have... Yeah, I agree with that. We can't have a new line in append file. That wouldn't make any sense. But flipping these two, that would be better practice. Right, run Haskell, append to do hs. Iron the dishes. Then we do it again, dust dog. Append to do, take salad out of the oven, and then we see, boom, done all the things. We needed to add a new line at the end of each line because getLine doesn't give us a new line character at the end. I guess the difference is that if we appended it at the start, we would get an empty line, right? There would be an empty line at the start here. Empty line, and then iron the dishes, and then dust dog, and then take the salad out of the oven. But there's an empty line at the bottom now, but... Ooh, one more thing. We talked about how doing contents, hgetContents handle doesn't cause the whole file to be read at once and stored in memory. It's IO lazy, so doing this, right, with file, is actually like connecting a pipe from the connecting a pipe from the file to the output. How do you mean? Just like you can think of lists as streams, you can also think of files as streams. This will read one line at a time and print it out to the terminal as it goes along. So you may be asking, how wide is this pipe then? How often will the disk be accessed? Well, for text files, the default buffering is line buffering usually. That means that the smallest part of the file to be read at once is one line. That's why in this case it actually reads a line, prints out the output, reads the next line, prints it, etc. For binary files, the default buffering is usually block buffering. That means that it will read the file chunk by chunk. Chunk size is some size that your operating system think is cool. There we go. You can control how exactly buffering is done by using cest function. Yeah, it takes a handle and a buffer mode and returns an IO action that sets the buffering. Buffer mode is a simple enumeration data type, and the possible values it can hold are no buffering, is that it takes every individual character, line buffering, or block buffering, which takes a maybe int. The maybe int is for how big chunks should be in bytes. If nothing, then the operating system determines the chunk size. Yeah. No buffering means that it will read one character at a time. Yep, that's what I thought. No buffering usually sucks as a buffering mode because it has to access the disk so much. Alright, so if you want to read, you can decide to read more, even with a text file, right? You could set block buffering. If you know that you're gonna need to read more than a line at a time, right? Think for our data types. On the advent of code, right? We know that we're gonna read and use the entire file. Every single character in the file is gonna be used. Wouldn't block buffering, if we make a big chunk, more efficient? Because it would lessen the amount of access we had to do to the disk. Right, because we did transpose, and transpose takes the entire file. Yeah, we did transpose on the entire file, and that is what we needed to do. Right, here's our previous piece of code, only it doesn't read it line by line, but it reads the whole file in chunks of 248 bytes. Okay, so main with file, something text, read mode, our handle is do. Here we go, set the buffering on our handle. Set buffering on our handle to block buffering just, right, gotta remember that, just 2048. Then our contents is this whole thing, and then we print the contents. Yeah. Block buffering just 9999999. Well, this infinite nines. Right, there is probably some in between, right? I'm not good at this, but I would assume that if we're using the entire file, this number would be the actual size of the file, and it would read all the data just once, because we would only need to access the disk once, but that access would be more, it would be a what, CPU heavy instead of reading disk heavy. I don't know. We would read a big fucking chunk to memory. That is what we would do. So maybe there's a sweet spot. Usually you don't know the size of the file, but you can know a ballpark, right? Because if you have it too big, you take a huge fucking thing and put it into memory. If you overshoot, right? If you take more than your actual file, that's overshooting on the memory. So you probably want to chunk it in some... Because with the block buffering, you would definitely overshoot at the last block. The last block would be overshot, I suppose. Colgate Tab says, if your goal is to minimize disk access, that would be the optimal solution, right? But that's... We learned that from playing Exapunks. That is just one way of optimizing your thing. And if that is our goal, usually that's not what you want to do. You want to find, if you're trying to optimize stuff, you want to find the bottleneck, right? And adapt to your bottlenecks and somehow do a balancing act to make it as efficient as possible. That is optimization, I assume. But I guess in most use cases, and actually any use case that I would ever end up in, we don't need to care about this at all. We can just go with the stock. Yeah, probably. I could just go with the stock settings and just have the line buffering, and that would be fine. But reading files in bigger chunks can help if we want to minimize disk access or when our file is actually a slow network resource. That's a good point. Yeah. Slow network resource. Again, adapting to your bottlenecks. Adapt to your bottlenecks, indeed. We can also use the hflush, which is a function that takes a handle and returns an IO action that will flush the buffer of the file associated with the handle. When we're doing line buffering, the buffer is flushed after every line. When we're doing block buffering, it's after we've read a chunk. It is also flushed after closing a handle. That means that when we've reached a new line character, the reading or writing mechanisms reports all the data so far, but we can use hflush to force that reporting of data that has been read so far. After flushing, the data is available to other programs that are running at the same time. Yeah. We're done with this. Now you can have it back, I suppose. That's why we need to make sure that we close the files and whatnot. Make sure that we don't end up with a non-flushed file. A problem. Think of reading a block buffered file like this. Your toilet bowl is set to flush itself after it has a gallon of water inside it. So you start pouring water. That's what you do in a toilet. You pour water in it. And once the gallon mark is reached, the water is automatically flushed and the data in the water that you've poured in it so far is read. But you can flush the toilet manually too by pressing the button on the toilet. This makes the toilet flush all the water, that's the data inside the toilet, is read. In case you haven't noticed, flushing the toilet manually is a metaphor for hflush. Oh, is it? I would never have guessed. Yeah. This is not a very great analogy by programming analogy standards, but I wanted a real-world object that can be flushed for the punchline. I mean, it's a pretty good analogy, I suppose. We already made a program to... Well, the analogy doesn't work because, well, you don't read the stuff that gets flushed out, right? Right, we already made a program to add a new item to our to-do list in to-do.txt. Now let's make a program to remove an item. I'll just paste the code and then we'll go over the program together so you see that it's really easy. We'll be using a few new functions from system.directory and then one new function from system.io, but they'll all be explained. Tab says, not if you're a normie. Wait, are we talking about the flushing analogy? It's not very good if you're a normie? Oh, you don't read the contents of the flushed toilet if you're a normie? Oof, dude. I mean, I guess doctors really like to... Oh man, that's gross. Right, anyway, here's the program for removing an item from our to-do text. Looking in on tabs, that's... Yep. Right, system IO, system directory. Is that for paths? And we got data.list. Oh, this... This was a program, yeah. This was a do block, look at that. Right, do blocks is fairly easy to read if you know imperative languages though, right? It's the normal way of doing programming, isn't it? Colgate on that. Alright, so first we open our file in read mode. Yep, and we get our handle and we take... Wait. Open file. Wait, open temp file. We open a temporary file. That's something new. I'm assuming this is system directory stuff. That our temporary file is in our current directory and its name is temp. Assuming that. And it gets a temp name and temp handle. Colgate tab says there are literal shit blogs in the interwebs. It does not surprise me. At the least. I've never read one. I get easily nauseous. Yeah, easily nauseous. So I wouldn't want to read one. Alright, so I'm thinking this is similar to opening a file, but we get the name and handle straight off. This is our to-do. And we read... This is our two files. We read our contents from this handle and let to-do tasks lines of contents. Okay, we separate them into their own lists. Numbered tasks, zip with... Oh shit. Oh, tab says, well, they are more about looking than reading. Of course they are. I mean, they have to describe consistency. Oh, let's get back to Haskell, maybe, yeah. Right, numbered tasks, we zip with... Wait, what do we have here? We join with our line, we join with this, and we show n... tasks. Oh, right, so n here. This syntax usually surprises me because this show n somehow becomes 0, 1, 2, 3, 4, right? So we get a line number. Yeah, from this lambda. Oh, it's not because of the lambda, it's because of the zip with. Zip with takes a function and two lists, right? Yeah, there we go. So we zip these two lists. There we go, and that's our n. And our line, right? N is our item from here, and our line is our item from here. And then we zip those two items together. That makes sense. It's just... I get confused by the syntax. It's like this. This parentheses should be more... It's the... No, it's reading lambda functions, I suppose. and functions that take functions as parameters. I lose track a little bit of what's going on, but we figured it out. So we number all the tasks for whatever reason. All right. Then we put string on a new line. These are your to-do items. Right. So we just print all the to-do items that we have. And which one do you want to delete? Right. Since we have them numbered, we can just take a number string. That makes sense. And we let the number be read number string, right? Because it's a string, we want it to be an actual integer. That's why we read it. So now we have an actual number. And new to do items is that we delete. That's actually it. Delete takes a... Right, it takes a list. That's our to do tasks, right? This is actually interesting. I would have guessed that it would have been easier to delete with our index, right? But instead, delete takes an actual item, right? Because this is the actual item that we get. We get one of our to-do values, we get one of our lines, and we erase that line from the list of lines. Oh, getting on tabs has figured it out pretty quick even. Oh, Flattery is gonna get you everywhere, call getting on tab. Thank you. Then new to do items, which we will unlines. Wait, we just print now age put string. Here we go in temp handle. So we create this in our... This is a little bit confusing. We take the result, right? This is, we have removed, deleted, if you will. We have deleted the task from our list of tasks, and we put them in our handle, and that is our temporary file, right? Then we close the to-do file because we don't need that anymore. And then we close the temporary file. Then we remove to-do text and we rename our temporary file to to-do text. Okay, so this thing here, this function is a bit weird, but I'm assuming that this is our path, and that is our current directory, right? And the temporary file is named temp. And this just writes. I wonder if it necessarily creates a new file. Or if we actually have a file named temp. Oh, it doesn't matter, right? It probably erases all the previous content from temp anyway. All right. At first, we just open to do text in read mode and bind its handle to handle. Right, because when we write to a file, we don't need to extract contents. We just have to write to the handle. That's what we did here, right? Temp handle, right? We put the string in the temporary handle, that's the file, and we take this string that we put in. That makes sense. Right, next up we use, actually, keep that in here so we can see that if we want to. But now my face is in the way for the text now, so let's not do that. All right, next up we use a function that we haven't met before, which is from system.io. Open temp file. Oh, it didn't take a directory. Mistaken. Its name is pretty self-explanatory. It takes a path to a temporary directory. Oh! it's not a temporary file, it's a temporary directory, and a template name for a file and opens a temporary file. We use dot for the temporary directory because dot denotes the current directory on just about any operating system. Oh yeah, it is weird. We use temp as the template name for the temporary file. When they say template name, that kind of implies to me that it will name the next file temp0, temp1, temp2, maybe not. Which means that the temporary file will be named temp plus some random characters. There we go, yeah. It returns an IO action that makes the temporary file, and the result in that IO action is a pair of values, the name of the temporary file and a handle. We could just open a normal file called todo2.txt or something like that, but it's better practice to use open temp file so you know you're probably not overwriting anything. Yeah. If we're going to create a temporary file, it's better to, yeah, use a temporary file. I wonder why we wouldn't use read-write, right? They introduced the read-write mode, but we haven't looked into the read-write mode yet. I'm assuming the read-write mode will just replace all of this bullshit and create its own temporary file and do all of that shit in the background. Maybe. We'll see though. Right, the reason we didn't use get current directory to get the current directory and then pass it to the open temp file, but instead just passed dot to open temp file is because dot refers to the current directory on Unix-like systems and Windows. Didn't they say that? Yeah. Dot denotes the current directory. Confused me, saying the same thing twice. Next up, we bind the contents of to-do text to contents. Then we split that string into a list of strings, each string one line. So to-do tasks is now something like iron the dishes, dust the dog, take salad out of the oven. We zip the numbers from 0 onwards and that list with a function that takes a number like 3 and a string like hey and returns 3 hey. So our numbered tasks are yeah. That we figured out. That was this zip, right? We join that list of strings into a single new line delimited string with unlines and print that string to the terminal. Now, note that instead of doing that, we could have also done map m put string line to numbered tasks. All right, because we could have mapped the action to just print. That would have worked. We ask the user which one they want to delete and wait them to enter a number, which was, I mean, you should have, which line do you want to delete? Number, they didn't have that, right? Which one do you want to delete? I guess the numbers should be able to figure that out, but I don't know. Actually, no, that would be in the help. In our program, we would have in our help. I don't know. No, we would ask for a number. If we're having a number, we should ask our user for a number. Let's say they want to delete number 1, which is dust the dog, so they punch 1. The number string is now 1, and because we want a number, not a string, we run read on that to get 1. And bind that to number. Remember the delete and exclamation mark functions from data.list. I didn't remember that. Right. This returns an element from a list with some index, and delete deletes the first occurrence of an element in a list and returns a new list without that occurrence. There has to be a function that deletes an item based on index instead of the first occurrence, right? Maybe not though, because it's linked lists, right? Maybe you have to go through the list to the first occurrence. Right, to do tasks, exclamation, exclamation, number is, we get the index of the list. Number is now 1 and returns dust the dog. We bind to do tasks without the first occurrence of dust the dog to new to do items. And then we join that into a single string with unlines before writing it to the temporary file that we opened. The old file is now unchanged and the temporary file contains all the lines that the old one does, except the ones we deleted. Yeah, I mean, so far, everything was pretty much spot on from my explanation, right? Right. After that, we close both the original and the temporary files, and then we remove the original one with remove file, which, as you can see, takes a path to a file and deletes the file. After deleting the old todo.txt, we use rename file to rename the temporary file to todo.txt. Be careful, remove file and rename file, which are both they are both directory management. Takes file paths as their parameters, not handles. Yeah, right, because we're working in our current directory. We're not actually working with the files. That makes sense, yeah. I mean, we are renaming the files, but we're not in the files. The name is outside of the file, if that makes sense. And that's that. We could have done this with in even fewer lines, but we were very careful not to overwrite any existing files and politely asked the operating system to tell us where we can put our temporary file. Give this a go. Did we ask? Wait, we asked our operating system to tell us where we can put our temporary file. Oh, is that... this function does that? It automatically adds some random stuff and it checks if the file exists or no? Maybe. But it was part of system.io. It was not part of system directory. Oh well. Alright. Let's give this a go. Yeah, and it works. It just shows that it works. These are your to-do items. Boom, we get those things. Which one do you want to delete? Boom, and it's gone. I would have, when adding stuff to the to-do list, I would have added the number straight away, right? So the number was always there, if that makes sense. Oh no, shit, that would mess it around, right? Because then we remove something and add something else, the numbers would be all off. It would be jank. Yeah. Well, Gitino tab says there is no built-in function, but it's pretty easy to write your own if you want to remove element by index. Is it? I mean, the whole thinking was that we don't have to iterate over the list to remove an element. which I don't think we can do. Can we that? I mean, remove an element without iterating over the list. Could we just... We have a list, and then we just pluck a thing out and return the rest of the list. What time do we have? Look at that. Oh, I was asking about this the other day. Command line arguments. It was indeed. Another cursed. He needs to go see a dentist. Yeah. But since we're reaching lunchtime, I think we do command line arguments the day after tomorrow or something like that. Yeah. I think that's it. So, yeah. Thanks for hanging out. And have a good one. Yeah, yeah. Cheers.